In this video, I will go deeper into the connection between group theory and physics. This is the same chart we seen in the previous video, but I just do different color on different group elements so we can easily see their relations. Now, let's take a look at another example. So instead of using triangles, I can try to form a group with some 2x2 matrices. So we know we should have an identity element in a group, so let's have the 2x2 identity matrix. And let us say we have another matrix in our group, which is 1/2, and then square root 1 minus 1, minus root 3, and minus 1. And then we can have one more element, which is similar, but root 3, negative root 3, minus 1. So we can use these three matrices to form the elements of our group. And let's use just the ordinary metric multiplication for the operation between the two groups. So let's check that these three elements actually forms a group. To check that, we want to make sure it satisfies closure, which means the operation of these two group elements will again be a group element. So in this case, we need to check that the product of any of these two matrices will be one of the three matrices. So let's draw out all the possible multiplications we can have within these three matrices. And again, this is the first action. So we want to multiply these matrices on the left of these matrices. The multiplication of the identity matrix is easy. It just gives you back the matrix itself. So indeed, the result of combining the identity matrix to any other group element will again be inside the group as a group element. Now, let's look at multiplying the red matrix on the left of the red matrix. We have minus 1, root 3, minus 1, minus root 3. So minus 1 gives us 1, and then we have to minus 3. 1 minus 3 is 2, and then divide by 1/4, divided by 4, so you get minus 2/4, and that's minus 1. For the next element in our matrix, we have minus root 3, minus 1, so that's root 3, and then another root 3, so you get plus root 3, which tells you that it is the blue matrix. You can go check and work out the rest of the numbers inside the matrix, and you will see that indeed the operation of these two group elements will again be another group element inside our group. For the blue acting on red, we can again minus 1 minus root 3, minus 1 minus root 3, so that is 4. And divide by 4, that gives you 1. And you can work out the next one, root 3 minus 1, and minus 1 minus root 3. So that's minus root 3 plus root 3 gives you 0. And you can work out the rest, and you will see that indeed it gives you back another group element. And for here, you can work out the details by yourself, and you will see that indeed these three matrices, along with the matrix multiplication, satisfies all the group theory requirements, and indeed they do form a group. Now, these two groups looks very different from first sight. These are triangles, and these are 2x2 matrices. It seems like they are completely different group. But wait, when you look at the color, you see that the relation between every two matrix element or every two group element is exactly the same. And remember from the last video, the group is just defined by the symbols G1, G2, G3, and the operation just a dot. It doesn't matter if you are using rotation after rotation or matrix multiplication. The group itself is not defined by how it looks like, but just the relation between every two group elements. So we see that at the group element relation level, these two are exactly the same. So they are actually the same group, but we're just representing this group in a two different way, one with triangle and one with matrices. So the reason that they look different is because they are different representations. But they are the same group. The group itself is an abstract object just defined by the relation between the group elements, and the way we can and there are many ways we can represent such relation between the group elements. So the group itself for these two are exactly the same, and the name is called Z3. And these two are two different representations of the same Z3 group. Let's give another example of a group. We can form a group by the number 1 and minus 1 and ordinary number multiplication. 1, 1 give you 1, 1 minus 1 give you minus 1, give you minus 1, and minus minus give you plus. So you'll see that indeed the number 1 minus 1 and just regular number multiplication give you another group. And this group looks different than this group. And in this case, it's not just the representation that's different. They are actually different in a group level itself. There are two different groups, and you can see that because the number of elements they have is just different. This one has 3 elements, and this one only have 2. So they are just two different groups. And the name of this group is called Z2. And we don't always need to use 1 minus 1 to represent this group. This is a representation of Z2, just like this is a representation of Z3, and this is another representation of Z3. So we see that the symmetry is defined by the group itself, but how you represent a group is another story. There are 2 layers. One is what symmetry you have, which is what group you have, and the next layer is how do you represent such group. So in physics, what we're doing is to try to describe the universe in a symmetric way. But to do that, we need to figure out what exactly is the symmetry of our universe. So physics is finding what group is our universe. We need to find out what exactly is the underlying symmetry of our universe, but the universe doesn't have to represent this symmetry in just one way. It can have different ways to represent the same symmetry. So we also need to find what representation of what group is our universe. So this is all physics is about. We're just doing group theory. This statement is of course wrong because there's a possibility that our universe has locality and is only locally symmetric, and globally is not symmetric. This is the case for general relativity, but if you're not doing GR, then for me, this is good enough to understand what we're doing as a physicist.